Okay, so hello everyone to this new episode of EagleFly, the experimental debugger. Today we continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. Today we'll continue making the disassembler, and if you'd like to follow along, please don't hesitate and join us. If you have any questions, you can post them on Twitter or YouTube, and I'll be there to answer. With that said, let's start with this. I will open the project. So you remember the last thing we did was that we finished disassembling one instruction REX with REX prefix included. So now we can just test it and see what happened in the debugger. Okay, so if we run this, and there you go. So you can see here, this is the instruction string for the x64 instructions. And well, we in the last stream we added these two instructions which have REX prefix included, and yeah, I mean that's pretty much it. That's the last thing we did, and that's what we're gonna do today as well. We have to finish REX prefixes, so let's continue with them. And one thing we can do now, we can try to find another instruction that has REX prefixes and see how can we disassemble it as well. So let's try to find one. So if we see here, we have the different modes for REX prefix. The ones we have used already are REX register and it was, this is the register one, and this is the memory register thing. Although we haven't used this one because the B or the base that goes on RM pretty much will modify this case here and change the register to an extended register like R8 or something. So that's something that we can do and see what happens, you know. So we can do this one with the base and see how we can use the B field. So we go back here. Let's add the instruction string for that case. Let's see. So we want something with the P. So we can say, we can even do it. Now we found that using the assembler itself can be really helpful to see how it encodes it, so we can do this better, because we found that if we use our own encoding, we have like this, we can have problems if we do it ourselves, you know, because we don't know exactly how the encoding works. So if we see a real encoding, we can see easily how it should be encoded. So let's say we have a move here, and I'm gonna say we have R8. Well, we can do another one, I guess. R13 plus displacement plus, let's say, I don't want to do the SIB because first the encoding for the SIB has to be different, you know. Like if it goes to the SIB on the index, we will need to change it a little bit, which we would do, of course, but we have to go step by step here. So my question here is that when we have REX, this should change to, shall we sign extend this 32 as well? And that's the last thing we did yesterday, because we didn't well, if I run this, we have 32-bit displacements that they are not sign extended. Probably the processor will do it for us, but and I mean, it would be okay if we do it or not, but in any way, the processor will do it for us, and it should do it anyway. So let's do that first. We don't have any problems with doing that kind of stuff, so let's try to do that first. I'm gonna say that. I'm gonna go to here. And sometimes, we have displacements that doesn't have an index, so the index is not gonna do it here. And as well, if we have here an index size, this is not totally correct, let's say. It's better if we do this like defective address. This one. There you go. So right here we have a byte, and since it's already a byte, we can just see and check the displacement on that byte. Right here we can have the same byte, but we have to move it a little bit, so it has to go up to displacement -1 and get that thing. Well, no, this is not correct. Now, I don't know if we have the reverse thing here that it's super useful in these cases. Reverse scan, bit scan, reverse, and this is a U32, so probably we want bit scan reverse core. We can, I mean, it's a U32, but the problem is that we are not like addressing. So it's, I mean, it's the same because we already know it. So you just say, hey, I'm gonna treat you like, oh my god, I'm gonna say I got a pointer of disp 32, it's gonna be disp, and then this is this, and this is that, and then we don't have to cycle to get it, yeah. And this is gonna be that. And so we have the offset. Even, I mean, we don't even need this bit-scan reverse at all, because we just have to do the same stuff as this one, you know, but the displacement is gonna be, I mean, I'm gonna get to the last one, let's say displacement -1, and that's all we get. So if you think about it, we're gonna have the effective address size. We have a displacement, which normally it's, if it's a 32, so it's gonna be 4. So we want to sign extend it by 4, you know, so it's just like this. And yeah, we double sign it so we just get the right thing there. And then we go to displacement -1 and we just bring it backwards. Okay, that's correct, that's okay. And this is just the sign extension thing, and we push straight into the buffer. Oh my god, oh my god. We compile, that's kind of hilarious, it's kind of crazy. Okay, so yeah, so let's test that and see what happens. Hold on a second.
Buenas tardes. Descansar. ¿Qué? ¿Cuándo? No. Fíjate, corazón. No.
All right.
Ya te digo. Bien, gracias a Dios. ¿Ustedes? Ya se vivió, ¿verdad? Ah, qué bueno. Señal de que ya se vivió. No, ella no se verificó.
So there you go, we have a displacement.
Ándale pues, me la saludas. Ok, bye.
And we have set data size 32-bit. And we got displacement -1 by, this is the most significant bit. Gracias. 1, 2, 3. Oh. There you go. So there you go, we have the displacement set, which is now sign extended as well to the effective address size. So we can do just the same thing with the other ones. Okay, so hold me a second. I will move the computer for a moment, okay? Alright, so I'm back here after we transition a little bit there. So yeah, so we disassembled correctly the first instruction, which is nice. So we signed extended correctly. So let's do the other one as well, which probably, I mean, it's gonna be the same stuff. There we go. Now we have RAD, RAX, blah 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 blah, and then the next round is gonna be this. I don't know which instruction it is. It should be REX 3222 33221100. Now we have REX RDX, which is not gonna have anything about that. FF00 should work as well. There you go. Now let's look about this. This is the let's see what's happening here for the fetcher. There you go. We should have 7 bytes of just F's. Just in case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, there should be 14. And then the by. So here you go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There you go. That's correct. Now the next instruction is a fat, so it's just whoa. Whoa, what is it? Where we are? This is the last place. That's kind of weird. Okay, one more time. Three 1100 FFFF00 00004 0000000. There's thanks. Okay, that's good. And the other stuff is gonna be the same thing. Alright. Now we can choose to print the word pointer, core pointer stuff, which it would be something useful, I guess. So yeah, let's try to do that. Yeah. because now we have an option to do that as well. So we know what we are looking at here. Well, we know it from this place here, but you know, for each instruction it has to be something different. So let's try to do that. So for doing that stuff, yeah, we have core pointer, dwell pointer. This doesn't need that stuff. This is gonna be at REX F1 2 3 4 5 6 an immediate that is 1/8. So I don't know what this instruction operand size is. It should be 32-bit. Well, let me see. Because this is, let me see the stream here. Where is it? Here we go. So we have 1 2 3 4. It's this one. This is an add with REX, and it's using, well, if we remember, let me go here back. So it should be an 8, isn't it? So this is like saying, I don't know, well, it's 80, let me put it here, and then we have 40, which is the month, and then we have OB, this is the immediate, and this is the displacement, which is a byte. So this is a mother M, or should be mother M. Now, why do we have REX printed that way? That shouldn't be the case, unless, well, yeah, probably it is, because we're in 64-bit mode. Is it valid in 64-bit mode? Yes, it is valid in 64-bit mode. So if we add the instruction and then we say, hey, we have a memory operand or register operand in this case that is 8-bit, so the operand size is 8. The immediate operand is 8 as well. So okay, that's kind of the matching here. So this should be I don't know how you call it, but it's like this byte pointer. So let's see if we can replicate that. So add plus F0, comma, this is F0, so probably that's the way. we have a displacement 8, then we have this OB. So let's see what the disassembly wanted to for us. It's a kind of funny instruction because it was by pointer REX. Now I don't know why it didn't set it like an immediate thing. So and what's the difference between this and this? Nothing. Okay. That's kind of weird, but well, the encoding itself, it's okay, you know, because we have an 80 there. So we have, where is it? No, this one. 80 80 08 40 40 0. Now he has 40 40 OH. Oh, here it is. Okay, 40 40 08, and then we have a 0. So it's missing this 0 0 0 0 40 40 40 08. Okay. So this is a NAD. It has an 80 there, in which case we have if I remember, where is it, a 40 and they have an 80, that means this is a mod RAM. So we go to the mod RAM and see what's going on. We have an 80, so we have EAX plus displacement. That's totally correct. But he thought it was a displacement 32 instead of a displacement 8. So that's interesting. That's not the difference. So yeah, I mean, it's just the way he did it. It's a little bit weird, but yeah. It's because if you think about it, well, 4048, well, here it doesn't mean anything, but 4048 should be just a displacement to the effective address. So yeah, even though we have an 8 there, it has to be sign extended as well. So door pointer, core pointer, by pointer, REX 404008, and that's it. So yeah, I mean, it's pretty much the same thing. So this is a by pointer. I'm gonna say add by pointer, blah blah blah, OA, OB, and then this FAT doesn't need anything there. This, on the other hand, needs an float. It pushes an M64 floating point onto the FPU register stack. So this is a 64 operand. So okay, what about the disassembler? Test that soon. I don't care about that. I'm going to do the FLD or or we can say this. Which, well, this is our own type, so it has to be more like this, real 8, and this I'm gonna say a displacement 32 if I remember, yeah, because we were using that thing. So we're using those as displacement, real 8, blah 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 blah. What about that? It seemed to be possible. Let's see. So we have an FLD core pointer 4040H. Okay. So yeah, they changed it to chord. He didn't think about if it was a floating point thing, which normally, I mean, if you think about it, I mean, this is kind of busted if you think about it, because I mean, he should know that it's a floating point thing. So I mean, you can, well, yeah, you can load a chord, yeah, that's possible, but the instruction, you know, if we go to FLD there somehow, so here, yeah, we have RM8 IM8, you know. I'm gonna move this because this is a little bit better. I'm gonna copy this. This is valid, and this is the, let's say, the mnemonic. Now these are the same, these are just the same thing here. These are the same, no problem with them. Now this, of course, we have to make the change there because this is not correct at all. So FLD, just that's correct, but this has to be, and let me do the EAX stuff here, which is the last one, because since we are in here, I would like to see it as well. 030500, okay. So we have 03, and we probably have this one because we have the mother M. So R32, run 32, which is valid on both. So let me copy this. That means that this has to be a word pointer, and let's go to the FLD. There we go. We get into it, and we are encoding for the FLD. It's the number 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. You have a DD there with a 4040x05. So this is DD 05. So it has to be DD plus it was that it had an extended opcode there, you know, which is okay. In the mother M we have this one, M64 flame point. So I guess it's okay to just say core pointer in this case, because yeah, we have an M64 there. And then the VM resume doesn't have parameters, so that's okay. XMM0, XMM1 away, that's okay. The shield left should be at word pointer, I believe. Let's see. We have I don't remember. It's the last OFA4 050003. This is the displacement. It's a 2-byte scale up code. 2-byte OFA4. We have this one, OFA4 RIB, but this is for the 1616, and we're thinking on the 3232 right now with an immediate 8. Shift R and 32 to left, and immediate 8 places while shifting bits from R32 in from the right. So shift to left, and then from arrow 64, so we can start building our own tables, like having the description, having the mnemonic and stuff, you know. And this is just the same or here. This is gonna be, well, actually I was wrong. It was, and then we can copy this table. That's the whole thing we want. And shape left RM32, that means we have a door pointer there, if any. And then, so yeah, I mean, so we have like a complete set of information. Then so yeah, let's get all the whole thing, I guess. This is the pointer, p-line R. There you go. These are really simple, but you know, on the new ones are gonna be just, or like for example the shift left double and stuff, which are different in nature. P-line R. Probably this needs to be like this. Here we go, and the one we have is this one. So yeah, the same instructions are the ones that need more descriptions. Let me put the charger here. And we have, I don't remember, DDE1, and let's see if that we have it here, the microcode. I'm gonna go back into there. And the one we have is a D8C1, D8C1, F add ST0 STI. Now Fukon, I believe, was the same thing here, description comparison ones here. And this is probably, I mean, if we want to disassemble to different assembly languages, this is not gonna be useful at all, but yeah. So well, and we have the moves and the adds. Well, the adds already done. We are just missing the moves. Now the Fukam, if I remember, is to make sure. It was this one, isn't it? well, since it's just DDE1, yeah, it's this one. This is the mnemonic. We shouldn't even print that. But yeah. There we go. And there's another one, of course, that is like, hey, full comments T0S21. Okay, so let's go to the move, and we already have the cache. So we can see we already, well, we have 3 of them. We have REX RDX, which has the encoding 4889D0. So if we go to the 48, no, sorry, 89, because that's the mother M. We have 89 plus 48, that means we have this one. We're moving RM blah blah blah. This is RAD door pointer. It's a 44. It's an 8B. It's an 8B. So it has to be one of these ones. We have the one with 64. And the other one is an 8B as well, but in this case, well, it's the same, see? It's just that we are moving from yeah, this is a tricky one because it's from the RAX, because in fact, well, this doesn't have, this itself is not R64. This is more like R32. So this is this one, but you got the idea, isn't it? There we go. So I mean, it was like a stretch work there, but now we have like the real information. We have some description that's kind of useful for us, for if you want to read that thing, you know. Even if we want to print this out, you know, like say, hey, this is the description. If you don't know what this instruction do, well, we can show you what it does, you know. And then we can go more descriptive if we want, you know. This is just like the thing that we found out there, which is super simplified, but yeah, you know. we can do this. Since this is the disassembler, it has to print out information, so the more information we have, the better. So you see here, well, we have the only thing that we are missing from the tables is the encoding of it, which um, mm, yeah, probably that's also useful. I mean, normally you understand memory register, register memory, floating point unit. I don't know. No, I don't know what this means, but it's a map set. Okay, but I'm gonna hold on there for a moment. Probably in the future we want to add that as well. But yeah, so that's the idea behind, I was just like putting all the information there. And so if we want to do that thing about the word pointer stuff, which is okay, we can do it. Let's go to the fetcher. And here I'm gonna say that before anything else, where is it? Over here, we have an effective operand size, which we are going to use in here to define it. Now let me think about this, because the REX should be checked as well, if that's the case, for printing this out, isn't it? Because we are making the resolution for the sizes and stuff. We have a data size 8-bit, we have a 32-bit, whatever. We have a 32-bit data size invalid, something like that. So that if we're gonna print a memory operand, we want to have like that kind of thing happen. It's not gonna be it's kind of useful, it's not like super crazy, let's say. You can imply from somewhere else, but sometimes it's, for example, this is chord, this is a byte, this is a chord or chord byte thing. So yeah, we can do it. Yeah, why not? Okay, so we need the effective operand size, and for that, if you remember when we do the fetch register operand thing, we make all this stuff to solve it, like REXB, are we looking at whatever, so the effective size of this stuff, whenever we're looking for REXB or whatever we're looking for something, is gonna define that. Okay, uh, so how can we do this? Normally the operand size is gonna be the thing. Yeah, it's gonna be the operand size, isn't it? Because the p just works with the extension of it, just to define which one we are looking for. But by itself, the size is just the size, the size that we got there is the size. So we're using the effective operand size, and that's the thing we pass there. And here we're gonna use just the same thing here and say well, I don't know, this is a little bit wonky but I'm going to do, I'm gonna say do we have word wall thing stored in there? Probably not. So probably we want to store this somewhere else, but whatever. For now I'm gonna keep it here, it's okay. Now these are not precise, I mean, since these are data types, they are not precisely the thing. This is, I mean, this is MASM. Which is normally the case. I mean, right now we don't have a, like, we follow the Intel thing in the way the order is going, but we are not following, we have to define which kind of assembly language we want to print this out, which I don't know. I mean, going for MASM is just like, well, these are the things, probably we want something else, something like, I don't know, how do you call M128? Probably like this, M256, and 512. So yeah, I mean, I don't want to deal right now with data types, so that's why I didn't do it. So yeah, probably we want to skip this and put here. Do output dependent types. I'm just gonna do that. So yeah, I mean, I was like thinking, well, we can do it, but I want to get into there right now. We can do that later. It's not like super relevant right now. So we can just do that. And I'm gonna leave it there, I guess. It's a rhyme. Let's compile. And so, well, let's try to do another instruction here. I'm gonna go to the test asm, and we got the add FLD. I'm gonna do the move, and now I want to have an instruction that uses the base. That means I need to do this R13, and I'm gonna use, well, without the displacement, why not, just like that. And then here are we could have even this. This is gonna need an operand size attribute prefix, which is okay, I guess we can do that. R13 as well, and I want this. Yeah, I like that. There we go, we compile. Let's see the disassembly. So we have a word pointer R15, R15, and we have RAW there. Okay. Okay, so this has a 66 operand override prefix. That's correct. We have a 45, which is the REX byte, which tells me that it has R and B. Okay, it has R and B. It's using R to have the rec use R, and we're using B to have it on the base here, so that's the way to have both R's, and then we're using both R's, and then we're having 66 that overrides the operand size override for the thing. So even though we are extending, we are using an effective operand size of 16. That means we have 8 W thing here. So yeah, and and yeah, that's the thing. And then we have a word pointer because that's the thing for the that's why it's word pointer, because it's in 16-bit. We're getting to 16, and yeah, that's it. So we have 45, 8B is the main of byte, 45 is the modern byte. This 45, it has a special, well, if it's 45, that means that it should be Whoa, that's a little bit weird. What's 45? This is a little bit crazy, isn't it? I mean, it encoded an 8-bit displacement that it's 0 to it. That's super weird. Super weird. Yeah, I mean, this thing is a little bit weird. I mean, it's okay, but it's just like, I mean, it's using 45 instead of just using these things. So why didn't it choose to use these ones? Of course, I'm using R8, but R8 uses the position on here. Now 45 is using a displacement. 45 goes on the mem and tells me that I'm using EBP plus display. EBP, well, it's because we're using R13, isn't it? So it's R8, 9, 10, 11, 12, 13. That's the reason we are using this one. Oh, look at this. This is interesting. Since it cannot use this one for 13. That's kind of funny. We cannot use this one for 13 because it's not encodable. You know, that's not possible for Intel. Okay, this is a nice problem. You know, it's like, oh, it's not encodable here, so I'm gonna add, you know, a 0 to that encoding and say, hey, this is the way we're gonna do it. It's gonna be R13 plus a displacement that's gonna be encoded as 0. Cool. That's the way that the assembler did it, and that makes sense. I mean, that's the only possible way to do it. We can do it with a 32-bit as well, but it would be just a bigger instruction for nothing of the displacement. So yeah, that's kind of nice. That's kind of nice. So let's follow that idea, that pattern there. I like it. So I can just do that. I'm gonna go in here and I'm gonna go to 0x. Oh my god. Here, this is gonna be 66. Then we're gonna have 8b. Well, we're gonna have 0x 4, and we need 5. We need 8b. We need 0x 4, 5, 0, 0. So 66, 45, AB, 45, 0, 0. Cool. Cool. That's so cool. Okay, so I don't know what's this, doesn't matter. We're gonna do that. Let's compile it. We do compile. So we don't need another entry because we're using the same one, AB. But now we have a 66 thing, so right now we don't do anything at all with that, so I believe it's just gonna do bananas, you know. So this is the problem that we probably want to get mandatory prefixing. I'm gonna move this, and I'm gonna put it here. So if I go to mandatory, it has 66, F2, F3. Those are the mandatories, you know. But yeah, let me try to solve this, you know. Okay, so here's where the fancy stuff comes. Right now, we don't know exactly how can we say if something is a mandatory prefix or it's just a standard override size prefix, you know. That's the problem. That's the thing we want to solve. So for knowing something more about that, you know, the mandatory prefix thing, most of the time is gonna come, it comes before REX, so that REX always comes afterwards, you know. So we have mandatory first, then REX, then the main up. That's the order. So that tells us that we have to have a cache. Well, we can solve it in many ways, you know. We can have a cache there that just, you know, push the bytes to some byte stream, and then we make the resolution, you know, like, hey, this is a mandatory prefix. This is, I mean, pretty much the same way as we do it for the entries and stuff, you know. Well, this is our, we have all this inline stuff, you know, which is, that's kind of interesting. I can even compress all this stuff, you know. But yeah, I will do that later. Okay, I want to see the whole functions being displayed, because I saw the part. I mean, they are really simple functions that they can be collapsed into one, probably, I guess. Mandatory prefix, there you go. What's this? Print instruction, that's okay. This is initializer, it's valid mnemonic entry, and that's all we do. So let me go to the table. So that, yeah, I mean, the mandatory prefix is something that has to be found. I mean, it's not truly important. This is AVX. We haven't got to AVX, so that's not important. Okay. And I don't have internet. Let me connect myself. Okay. For example, here comes information about which instructions have the possibility to have the lock, for example. oh, this is kind of nice. Well, this is the same thing. Okay, so we're like, oh, this is kind of let me see. I don't know if this is veridic, but yeah, we can try it anyway. So the branch hints are only supported by Intel since the Pentium 4. Whether using them on AMD architectures has any positive or negative effect at all is not known. So I mean, the question is, well, this is for later, but can we find out reading the executable if the if the default flag for the code segment where it's gonna be loaded, it's gonna have the bit set or not? I mean, it's something that the executable could define. Who knows? But yeah. Okay, so well, this is a helpful thing for the prefixes. They don't have they don't tell me about the they have the mandatory, the REX, and the opcode. So normally rather it's a assembly instruction, or rather something else. For now we can assume that's just a assembly instruction. I don't know, like we can just say we have these instructions as well. So yeah, I mean, now what I think about the, oh nice, I didn't see this. Registers and codes in the 4 bits. These are the whole thing. The segments. These are 80-bit, x37, 64, 128, 256, and here is missing 512, so probably this is a little bit old. It has a segments, 32-bit control, 32-bit debug. We have AH, CH, DH, BH. Where is it? Oh, here. So remember, yeah, with 32-bit we cannot get AH, so it has to default to SPL and stuff like that. Okay, this is a nice thing. I'm gonna save it. So for now, It's gonna be janky, I know. Don't do this at home, please. But well, yeah. Well, we know there are simple instructions. For now, we're gonna say, hey, we have a simple instruction, or hey, we have an operand size, you know. So let's kind of think about that. So OF, well, we don't care about OF. It's okay. Probably in the future we're gonna care about this, but for now, we're gonna do that. So so this comes first, so that's why it has to go there. And I am gonna say we can do it like saying first, like we have an operand size thing. Even though we don't have an operand size thing, then we have an REX prefix. But since we can have both, you know, we can have a mandatory prefix and we can have this, you know. So these you know can be and come before, so it's not that it's gonna come here, well, following the order here, of course. So it has to go with something like that, and I want to say, I'm just gonna move along here and say, I'm gonna say something like that. So we want to make sure that whenever we don't get this, but we do have this, so there's three possibilities. Well, there's four. We have none of them, we have one of them, or we have the other, or we have both of them. So we have four possibilities there that we have to address. So this is where the complexity starts to mangle. So let's say for now this is not going to be correct, but for now, just because of it, you know. Well, well, you know, I mean, I'm gonna do this thing, but since we're running right now out of time, I'm gonna do this. Let's say we have on the test system, so we can check. We're gonna check instead of the word, we're gonna go the same thing here, and that should be it. You know, you can do alright and just do the check in there. And there we go for the mandatory prefix stuff, which is gonna be something, you know. So yeah, I was like, well, you know, we can do it, we don't. Well, it's gonna be something by its own. So, well, I can just say that. And this is gonna be for the AB 4500. Okay, so let's go and solve this one instead. So it's 4D. This is the, we don't have a 66 as before. This is the REX, AB main byte, mother and byte, and the interesting thing there. Okay. So I'm gonna say, hey, we're gonna hold on here. And this, it's a 4D. That's because we have 8 So we have 8, 19, 9, A, B, C, and 1. So we have W, R. Okay, this has the whole thing playing around. It has, well, it doesn't have X, but it has W, R, and B. Okay. So we have for the AB 4500. So that wouldn't get so much problems, you know. And let's do it. So we can run this, I guess. And we have REX, which has 1101. That's correct. We get that, and we say, hey, we got that. We got the entry, which is the same as a move 01, blah blah blah. Yeah, that's correct. And we fetch the memory theme, which for this case is just going to be 1 operand. Well, it has a displacement 8, so there you go, we have a displacement 8. And then we say push a string. We have SAB, we go and fetch here. We have R13, that's correct. Boom, boom, boom. Then we got push string to buffer, there you go, plus displacement. That is 8-bit. We have a byte, sign, 0. Now we're gonna sign extend it to the thing, which is alright, I guess. It's just gonna be huge. And then print the value there, it's another 0. Now here we're gonna have R8. So yeah, I mean we are already doing the B as well, because we already added, so that's good. So now we don't care about that, but yeah. So on the next stream we're gonna do the I don't know if we do the SIB first and then we do the whole thing about the yeah, because that's gonna be a whole stream. So yeah, I'm gonna hold with the mandatory prefix and stuff like that. But it was good to have some info about it, you know. So if we continue, let's continue, because well, we can print them all. R13, REX, blah blah blah, blah blah blah, blah blah blah, blah blah blah, blah blah. This looks good. Oh, it doesn't look anything crazy there, you know. We are just using the whole thing about the R and B, and later we can do SIB as yeah. So the next thing we're gonna do SIB, and with that we can just finish REX, which is nice. So yeah. So just before finishing, let's match the string to the thing we got before. Which is on the disassembly. We have array, core pointer, REX, blah blah blah. and then we have array t, array x, 0033221100, and then we have array x rdx, array x ffop, f at st0 st1, for comma st1 st0, for the core pointer 004. Then we have the beam resume, pliner, 8, shield, eax, o3 at eax to a pointer 000. Okay, so then, yeah, that's good. That's good. And yeah. Okay, so let's just copy this. Well, I'm not gonna copy because I want the types here. So I'm just gonna put the move r8 r13 plus some displacement, which in fact, well, so in fact we can we could try to do the other one. So if you remember, well, I don't know, let me see, SIB, where's the SIB thing? Where is my, no, it's this one. Yeah, so R14 is not gonna be possible. So, for example, R12, is it possible to do it? Let's see. On the test asm, where we change it to R12. So it's the same, we're using both of them AB, but the mother M now changes, and we're getting 04, and we're getting a 24 displacement. It's a little bit weird. 808008 4040 0000. Add by pointer REX, whatever will be. Yeah, that's correct. So why did we choose this 0424? Let's see the mod ran by. We have 04. Oh, it used the SIB. Okay, so we have 04. That means that we are using the SIB, and then the SIB it's 24. That means that we have non-scale index. We have an index which is 100. That means we have none, and we have it on the 24 because that's really intelligent. I mean, it has to find a way to do it, and if you are doing with the extended, it has just to fill the whole thing, you know, because if you think about it here, 9 10 11 no 8 9 10 11 12, this is R12, so it's encoded on the base, you know, it's just the base, and that's it. We are not getting anything else but the base, you know. So that's interesting. That's really interesting. So we're gonna do that tomorrow because that comes for the SA. Now it's the SIB, but the base goes with the okay, yeah. Remember that the SIB goes I mean, the base can go with the REC or the SIB, so we can change the base to this uses the base with SIB, which is nice. Which is the next one to do, isn't it? The next one to do uses the base on SIB, it uses X on index, it uses R on the REC, and stuff like that. And finally, but not the least, we have the REC inside the main opcode. Alright, I like that. So please, if you have any questions, post them on Twitter or YouTube and I'll be there to answer. Please make your questions related to the thing we did today and I'll be happy to answer them. Yep, I would say thank you very much for coming and I will see you all on the next stream. Take care.